Thank you. Right, hello everyone. I know that I'm the only thing behind you and the lunch, so I'll take my time. Today I'm going to be talking about how we can make our Angular applications faster. So, yeah, as you already know, I'm co-founder and CTO at rhyme.com, where we're building a platform which, by using virtualization in the browser, is going to help you to build scalable and more consistent workshops and corporate trainings. In my spare time, I'm doing a lot of open source. I'm a former member of the Angular mobile team and co-author of the official Angular style guide. I'm also maintaining Codalizer and Angular Seed. So today, our focus is going to be runtime performance. I know that a big issue is reducing our bundle size further and improving our network performance of our single-page applications, like reducing network requests, for instance. And there are a lot of smart people already working in this direction. For instance, we have the Google Closure compiler team who are constantly dropping the bundle sizes. We have the Webpack team doing similar things. And on top of that, we have the Angular CLI team who are combining best from these two worlds in order to provide us a very well-encapsulated build. However, the runtime performance is entirely in our own hands. And today we're going to see a couple of practices which are going to help us to have better user experience and 60 frames per second UI. For this purpose, I built a very simplified business application which in general incorporates a lot of performance issues that I faced over the past couple of months developing business applications with Angular. So this very simplified business application is as follows. Basically here, as you can see, we have two lists of users. And in these two lists of users or employees, we have two departments. We have sales and R&D. For each of these departments, we have the list of the employees with their names and with some numeric value. This can be considered, for instance, the performance data of the employees, which goes through some very heavy computationally intensive business calculation. And on top of that, we have an input where we can enter new employees, basically type their name there. So that's the application, pretty simple. And we're going to see what performance issues we're going to face inside of it. And here is its component structure. We have an app component, which actually wraps our entire application. So this is the root component in our application. And we have an employee list component, two instances of it, one for the sales department and one for the R&D department. Here is a template of the employee list component. So we have a text input where we are using the banana in a box syntax for two-way data binding, where we are binding the value of the current input to the label property declared inside of the controller of the employee list component. And we also have a material design list items. So here we are iterating with the ng4 directive over all the individual list items, over all the individual employees, and rendering a material design list item for each one of them, where we are printing, using the interpolation syntax, the name of the employee and also calculating some numeric value. Let's think about it as performance. And here is the controller. So an interesting thing about it is that we're getting the data as an input. This means that the app component, it holds the entire state. It holds both the list for the sales department and for R&D department, and it passes this data basically to the two instances of the employee list component. We can think of the app component as, for instance, container component in sense of Redux. And we also have the calculate method, which in this case we are mocking the business calculation with Fibonacci, because we don't have to couple ourselves to something specific. We're going to just introduce additional complexity in this already simple business app. The good thing about Fibonacci is that it is purely a mathematical function, something similar to what we would use for calculating performance or just different formulas for aggregating information, for instance, like standard deviation or something similar. And in this case, we're implementing Fibonacci in the most inefficient way. That's on purpose. We're basically slowing down artificially in order to see the performance impact even further. As recap, we can say that we have an app component and two instances of a list component where we have very computationally intensive thing going on for each individual list item inside of this component. Let's see how this behaves with real data. So here we have a list of employees, actually two lists of employees, in total 140 entries. And for these 140 entries, we can try to add another one by using the input for the sales department, let's say. Here is the user experience. So yeah, we're typing right now. How many of you have had similar experience? Nobody? Oh, OK, a couple of you, yeah. Yeah, I have had similar experience as well. That's why I came up with this example. And it was kind of a struggle to improve the performance. But after figuring out in order to figure out why it is actually that slow, we can open Chrome DevTools, take a look at the profiler, and see that we're invoking the calculate method instead of the employees list controller very often. Let's see how often exactly by just adding a simple console walk statement inside of it. So we can see that we're actually invoking it very often. Every time when we start typing something inside of the input, we're triggering two events, key down and key up. And for each such event, we're recomputing the performance data for each individual employee, although we have already computed it, right? So it doesn't make a lot of sense. Do you have any ideas for optimization where we're going to recompute the performance data for each individual employee in the list only when we get a new list from the parent component? Any ideas for that? Yes. All right, on push. Yeah, I heard that a couple of times. That's a pretty good idea. Yeah. We can do that as well. We're going to reach this phase in a bit. So on push is a very good start. That was actually one of my first suggestions when I was optimizing my application as well. The on-push change detection strategy will allow us to invoke the change detection of given component sub-tree when we get new inputs for any of the components, for any of the inputs of the component. So that's very convenient. This basically means that, well, let's just try to explain this in terms of, in functional programming. We're going to model our entire application by using functions just for a second. So this is not Angular. This is just a model of our employee list component. We can think of the employees list component inputs as arguments of a function. And we can think of the result of a function, the function itself, as the actual user interface rendered by the employee list component. So here is the example. We have our employee list component, which is the function f in this case. So again, this is not Angular. This only aims to explain in simple ways when the on-push change detection is going to be invoked. And when the first time we pass the input for this function, when we pass data the first time, we're going to invoke, trigger the change detection, because we're getting a new reference to the input data. Previously, its value was undefined. The next time, when we push data, when we push something, employee 2, in the data list, the change detection is not going to be triggered. Because we're getting the exact same reference. We're just modifying the data structure pointed out by the reference, which is held by the data constant. And finally, if we provide a copy to this data structure, we're going to get the change detection triggered. So that's it. This means that passing a new reference is going to trigger our change detection. Does this mean that we need to copy the entire array every time when we want to trigger the change detection or when something inside of the application happens? Well, that's going to be a bad idea. So there are a couple of reasons for this to be a bad idea. First of all, we're going to allocate so much additional memory which we are actually not using because it needs to be deallocated from the garbage collector the next time. And second of all, we're going to perform a lot of very heavy computation. We're going to iterate over the entire list in order to copy all the list items. We have a better solution for this. We can use immutable.js. Immutable.js is a collection of data structures developed by Facebook, which provide us two very handy features. First of all, every time when we modify a given data structure, we're going to get a new reference. So we're actually not going to modify it. Instead, we're going to get a new reference. We're going to get a new object, which has this modification applied to it. And on top of that, we don't need to copy the entire data structure, because immutable.js is implemented in a smarter way, where we are reusing as much as we can from the previous version of the data structure itself. Let's now see how much faster we got after we optimized our application with on-push and with immutable data. So here is the typing. Maybe it's slightly faster, but it doesn't look great, right? So in order to measure the performance difference between the previous application, non-optimized one, and the current one, I wrote a couple of end-to-end tests with Protractor and run bench press, which is a very neat feature, very neat library from the Angular team for performance benchmarks. And here is the result, basically. We can see that we are almost 3 times faster. So at least 2 times faster, but we are still very slow. And let's see why. So here is our sales department, and we're trying to add a new employee inside of it. We can see that the change detection gets triggered very often. So every time when we key press, we're triggering the change detection at least twice for all individual employees, even for these whose performance information was already computed. However, this time we're at least reducing the change detection only to the sales department instead of to the sales department and the R&D department itself. So in the perfect scenario, we would want to compute only the performance data for the new employee that we are entering, not for the already existing employees whose performance data we have. And we're triggering the change detection actually because there is one more catch in the on-push change detection strategy. It is going to be triggered also when an event inside of this component happens. So there are a lot of events going on there. We have key up, key down, so the change detection is going to be triggered on each one of these. In order to fix this, we need to do some refactoring. So we're not only going to make our application faster, but we're also going to enforce better separation of concerns. In this case, we have the app component, the employee list component, and also we're decomposing the employee list component to the name input component, which is only responsible for entering the names of the new employees, and to the list component, which just lists the individual employees and has function for calculating their performance data. And here is how much faster we got right now. So much smooth, right? Actually, that's what I would expect to have from the beginning. It's really so much faster. And here is how actually much faster it got. So maybe more than 100 times faster. On the right, you can see how much faster we got with on-push, and the left one is the unoptimized version. All right, so we optimized typing in the text box, which was something which we definitely should do. Now let's see how fast is adding and removing items. So when we add a new item right now, what happens is that we're recomputing the performance data not only for the new item, but for the already existing items as well. This happens because when we add the new item, we are applying mutation on top of the immutable list. We're getting a new reference, so we're triggering the change detection for the entire component. We're recomputing everything from scratch, although we want to compute the performance data only for the new item. In order to optimize this, let's take a look at the Fibonacci implementation. The good thing, again, is that it is based on a mathematical function, just like most other computations that we're going to eventually perform, like standard deviation or whatever other performance information we want to compute, and however we want to compute it. So it has two properties. First, all such functions, they don't produce any side effects. So we're not going to send any XML HTTP request through the network or lock anything inside of the console or like touch local storage. And also they return the same result, the exact same result every time when we invoke them with the same set of arguments. In the world of functional programming, such functions are known as pure functions. And on the other hand, in Angular, we have pipes. Pipes are usually used for data transformation. Somehow of data transformations. And we have both pure and impure pipes. Pure pipes, an example for pure pipe is, for instance, the decimal pipe. An example for impure pipe is the async pipe, which holds some state. So that's why it is impure pipe. And Angular does some very neat optimizations for the pure pipes specifically. So for the pure pipes, Angular is not going to re-average them unless it detects that we have passed new arguments to them. Otherwise, it is just going to keep the previous result that they have returned. So this means that we can eventually apply some kind of caching by using pure pipes in our application if we encapsulate our business computation inside of a pure pipe. And here is how we can do that. We can just define a very simple calculate pipe where we're delegating the calculation to our business calculation, and that's it. And we need to update our list component in a very simple way. Instead of just invoking the calculate method defined inside of the list component class, we just need to delegate this execution to the pipe. That's it. Now let's bench press this with bench press and see how much faster we got. So this is an automated test. I wish I was that fast. And after running this for a while, we are going to figure out that we actually went about 100 times faster again. So that was pretty efficient. Now we have very efficient typing in the text box and very efficient way of adding and removing items. Let's see how fast the initial rendering is going to be with 1,000 items. So here it is. We downloaded all the resources already from the network, and now we're waiting for the app to be rendered, and waiting, and waiting, and it's done. So it took it about 9.5 seconds in order to get the initial rendering, which is slow. Imagine we optimize our application a lot, like we have bundle which is only 100K, and we download everything for, let's say, 100 or 200 milliseconds. So we have everything already in the browser, and into the browser it takes 10 seconds to render the entire UI. So this is very slow, and it doesn't matter how fast we get in terms of network performance. If our computational performance, runtime performance is poor, our UI is not going to be very good either. In order to optimize this, we can take a look at our data. So this is not a silver bullet, which is going to work for any application, but usually getting familiar with our data is going to help us to do that. In this case, we can notice that we have employees with very similar performance data. We have Fibonacci of 27, Fibonacci of 28, and 29. So in general, we can conclude that we have samples from a very small range, and during the initial rendering, we recompute the same data multiple times. Well, solution is just applying caching in this case. And in the world of functional programming, this is known as memoization, as someone already mentioned. This is possible for pure functions, because these functions should not produce side effects, and they obviously should return the exact same result when we apply them to the same set of arguments. Here is how we can apply memoization. We can just use memoize from Lodash and invoke memoize with argument our function. This is going to return a new function, which is going to apply memoization. So every time when we invoke the new function returned by memoize, the result returned by the internal function is going to be cached, and the next time it is going to be returned directly from the cache instead of recomputing it. All right, so here is how much faster we went. We downloaded everything, and we're still waiting to be rendered, and it's rendered for about 3 seconds less, which is a bit better. So we got about 30% improvements, which is still not bad. We're still computing very big values. And now we might be wondering, what is the difference between pure pipes and memoization? Why we are getting better performance when using memoization instead of pure pipes? Well, here is why. So with pure pipes, when we have to calculate the result of 27, for instance, we're going to directly delegate the invocation to Fibonacci of 27, which is going to return a result. The next time, when we invoke it for the second entry, we're going to get the exact same result, following the exact same process. First, calculating Fibonacci of 27, and after that, getting the result. Same for the third one. The optimization that we're going to get with pure pipes is that on the next tick, Angular is not going to re-evaluate these expressions, since we're passing the exact same arguments to the calculate pipe. That's the only optimization that we're getting. However, with memoization, we're getting this, and on top of that, we can also cache the result once we have computed it. So we're caching it in some kind of a global cache, instead of a very local one, what we do with pure pipes. So the next time when we want to compute calculate of 27, we're just directly going to look in the cache and get the result from there, and the same the third time. We can notice a pattern. So on push performs some kind of memoization. Pure pipes performs something like memoization as well. On push performs something like memoization because it is going to memoize the result of the last rendered component for the last rendered component subtree, only for a specific place in the DOM, only for a specific place in the component tree. So if we have multiple instances of the same component, each needs to be memoized separately, and also only for their last input. So we don't have cache, like global cache, for the inputs of the components. Well, now we're going to take a look at the final technique, which is a more advanced one. So if you're not completely familiar with the APIs that we're going to take a look at, don't worry, I'm going to try to explain them in details as much as possible. So we saw that we're using ng4f quite a lot in order to iterate over our list. And here is how it works. So the most important thing at this point is that it accepts a single argument in its constructor of type Iterable Differ. This Iterable Differ implements an algorithm which based on two lists, returns the number of modifications and the type of modifications between the lists. So if we have list A and list B, the iterable differ is going to return the number of items added to the list A in order to get list B, the number of items added to list removed from list A in order to get the list B, and the number of items which have changed their places. So that's it. And of course, the indexes of these items. So when the change detection runs, we're going to get the ng do check hook invoked. We're going to find out the differences between the current state of the data structure we are iterating over compared to its previous state. And based on the modifications, we're going to apply some transformations, like some animations, for instance, in order to visualize the difference. This means that the iterable differ is going to check whether the data structure has changed as a consumer of this data structure. So it is just thinking about it as a black box, doesn't know anything about its implementation. This means that it needs to perform at least one iteration on top of it, which is a linear complexity. But the data structure knows best whether it has changed or not, right? So we can encapsulate these changes inside of the data structure itself. We can implement a data structure which keeps track of the list of changes which have happened inside of it. Also decorates the already existing immutable list in order to have the same immutable behavior. And when we're applying a mutation on top of the data structure, with just constant complexity, we can push all the changes which are happening inside of the linked list. In order to make this data structure play well with JavaScript and Angular in general, we can just implement an iterator. So this data structure implements the decorator and the iterator design patterns. Basically, we built a data structure which is optimized for Angular, and in order to take advantage of it, we need to implement a custom differ. So this custom differ now with constant complexity only by touching the changes linked list in the data structure and know what has changed. This reduces the complexity a lot and improves the performance when we have big data collections. This data structure is also somehow inspired from persistent data structures. They are usually implemented in a completely different manner, but still they somehow keep track of the different versions of the data structures themselves. So persistent data structures are something very cool, which allows us to do some time traveling and like forking different universes. So they are pretty cool. I'll definitely recommend you to take a look at them. And here are the performance benchmarks with our new implementation. We can see that we're performing about 1/3 faster, which is still a decent improvement for big data collections. Well, the learned lessons from this case study are that, first of all, there is no silver bullet, which is going to help us to optimize our runtime performance in every case, unfortunately. There is no magical change detection which is going to help us do that. In order to perform a meaningful optimizations, we would need to understand our component structure very well, understand our data, and apply specific to our application benchmarks. And of course, last but not least, get inspiration from computer science, because that's a constant source of wisdom. I also wrote a book about Angular. If you're just getting started with the framework or switching from AngularJS to Angular, you can give it a try with this 40% off discount code. And thank you very much for your attention.